Hello, so my question was for homework 8, question 10, and we are told to consider the vector field F, which we are given here, and we're asked whether this vector field is conservative, and if it's conservative, we are supposed to find the function of f, small f, so that the vector field F is the gradient of small f. And then once we find this small f function, we are to use our answer to evaluate this right here. So a vector is considered conservative if it is the gradient of some scalar function such that the vector field F is the gradient of small f. This small f value here is also called the potential function of the vector field F. So that's the potential function of big F, which is the vector field F. And to test for whether a function is conservative or not, we are going to assign values of P and Q to our vector field here, and then we are going to find the partial derivatives, and if the partial derivative with respect to the partial derivative of q values, which is our second one here, with respect to x, equals the partial derivative of our p value with respect to y, if those ones are equal, then this vector field is conservative. So we take our q value here, we find the partial derivative of q, which is this value here, with respect to x, and we're going to find that that is 4. And then we come to our p value here, we find the partial derivative of p with respect to y, and we're going to find that that is 4. So as we can see, the partial derivative of q with respect to x and our partial derivative of p with respect to y are equal. So this vector field is conservative. So once we find that the vector field is conservative, this means that our field vector here is equals to the gradient of small f with respect to x and the gradient of small f with respect to y, which means that the first value here, which is our p value, is going to be our partial derivative of small f, which is our potential function, with respect to x, and this q value is going to be our partial derivative of small f with respect to y. So now our job now is to find this potential function f, which is going to make this true. And to do that, we are going to integrate. So we are going to integrate this first one with respect to x. We're going to integrate the second one with respect to y. And you can see that's done here. So the partial of small f with respect to x, dx, has been integrated here. This one is going to give us the x part of f, our potential function. And then this one, fy dy, is going to give us the y part of our potential function. So when we do the x part of our potential function, we get 3x squared over 2 plus 4xy plus g of y. G of y, the reason why we get that is because when we integrate with respect to x, there's going to be a constant, and the constant is going to be in y values. So that's why we have the g of y over there. And when we do the same thing, when we integrate with respect to y, we're going to have a constant in terms of x. So we have 4xy plus 7y squared over 2 plus h of x. Now we combine these two together so that we can get the overall f function, which is going to be 3x squared over 2. So you take that one, it's here, it's not here, so you're gonna put it down there, and then 4xy is in both these two functions here, so you just take one of them, and then the remainder is the 7y squared over 2, which is right here, and then you add the constant k. which is going to represent the constant for this whole function. Now this is our potential function that we have found from integrating both with respect to x and y. Now this potential function here, we are supposed to use it to evaluate this line integral along curve C, and then we are given the RT equals to t squared I plus t cubed j with those intervals there. And to do that, we are going to use the fundamental theorem of line integrals, which basically says that if you're given this field vector, which is the same as the gradient function of small f and then dr, it's going to be the small f x of b y of b minus small f x of a y of a, which is very similar to the fundamental theorem of calculus that we learned in another calculus class. Okay, so for our particular case here, we were given that r of t equals to t squared I plus t cubed j, which basically means that our x of t equals to t squared, and we're given the t intervals from 0 to 3, or rather 0 to 3. So our x of t equals to t squared, which is 3 squared, which is equals to 9. Our y of t equals to t cubed, which is equals to 3 cubed, which is 27. So these are our b values. If we were doing a, b, these are our b values, or rather where the function ends. Our a values are the zeros. So for our a values, then we will have x of t, which is equals to 0 squared, y of t equals to 0 cubed, which is 0. So we will have our a values will be 0, 0. Our b values are 9 and 27, as you can see here. This is the potential function f x y, which is f 9, 27. And then f x y is also f 0, 0, which is our a values. So we are subtracting the b values. We are taking the b values and then minus the a values according to the fundamental theorem of calculus right here. And you can see that the potential function f and then x of 3, y of 3, minus potential function f, x of 0, y of 0. So what we are going to do is basically just plug in this information here. So we have f, x of y is f 9, 27, which basically means the x values are 9, the y values are 27. So we are going to plug them in our potential function here. So where there is x, we're going to put 9. Where there is y, we are going to put 27. And once we do that, we are going to get this here and then minus 0 because of the 0, 0. So that just is going to be 0. And once we evaluate that, we find that the value is 3,645. Thank you.